John von Neumann's main contribution as a scientist, in my opinion, is his work on artificial intelligence. In particular, his work on computation and electronic brains. Now, after having read his biography, I think it's paramount how important his contributions were, in particular, his ideas on probabilistic logics, which influenced John McCarthy, who then coined the term artificial intelligence in 1955, so about 3 years after the lecture at Caltech, which inspired McCarthy to actually get at AI. Now, I want to draw an arch between von Neumann, John Hopfield, and Richard Sutton. I think those are the three main characters in the evolution of AI. I'm omitting other people here, but fundamentally, I think those are the most important scientific contributors in terms of creativity, and I'm going to attempt to explain why I feel that way. So I think von Neumann set the stage because during the Manhattan Project, he was forced to do the kinds of mathematics that at that time were just unthinkable. Calculating the scattering of neurons, predicting the evolution of a neutron bomb in a hydrogen setting. Things like that are incredibly computationally intensive. Even today, probably, we wouldn't be able to do the kinds of computation that are necessary to predict with high certainty what happens in a hydrogen bomb when neutrons scatter and create a chain reaction and then create an implosion that creates an energy surplus that then potentially influences a fusion. Things like that were people working on in the late 40s and early 1950s. They were computationally so intense that von Neumann automatically was inspired to think about more interesting electronic ways to do this, very similar to Alan Turing, who developed lots of interesting computational theories just because he wanted to crack the Enigma code of the Germans. Now back to von Neumann and his paper, links in the show notes. I think it's a seminal paper for many reasons, not just the least because it inspired John McCarthy, who then became a big figure in AI and professor at Stanford until 2000, to proliferate the field. Now, fundamentally, what's common between von Neumann and Hopfield and today Sutton is the idea that with simple rules you can create complex systems that are learnable. I think that's in my opinion fundamentally what's so powerful here. So whether it's the rules that are predetermined, like in a Stephen Wolfram type of way, which is interesting from a maybe more intellectual academic perspective, but from an engineering perspective, of course, those rules are not put in the system, but those rules are learned through interaction with the environment. That's the key. In the probabilistic logics paper, Neumann talks more about error correction and deterministic outcomes in probabilistic systems. So he's kind of laying the foundations for engineering computer systems that are inherently unstable and make them stable. So that's of course something also that is akin to today's quantum computing research, which is very similar because the hardware is very unreliable. We have to work with error correction and things like that. But fundamentally, I think the idea that you can start with unrelated, simple connections or neurons or components that have input, and then build from there a system that interacts with the environment and creates a much more complex intelligence. That idea, I think, is paramount and gets carried over in John Hopfield's 1982 paper, which is titled Neural Networks and Physical Systems with Emergent Collective Computational Abilities. So here, Hopfield really lays the foundation for what is to follow. He uses thermodynamics and energy as a optimization function for neurons that evolve throughout in a system through time with exposure to the environment again in a learned way. And he is kind of setting the stage for what today we call loss function or reward function design, where we want to minimize some sort of loss function, or in Hopfield's terminology, minimize the energy state. So he's inspired by physics. He also crosses the bridge between neuroscience and physics. He gets the Nobel Prize 2024 for physics. He really lays the foundation for AI, and this idea that you can have very simple components, let's say neurons, that are connected, and through their connection actually create a memory, create some sort of understanding of the past, and then that can be tapped in for, let's say, inference or for future learning. So that fundamental idea is John Hopfield. Now, Richard Sutton, and in particular his oak architecture that he presented this year, and his work with the bitter lesson, the essay in 2019, and most of his career actually has worked on very similar concepts, very simple rules that are learned, that create complex behavior through exposure to nature. So I see those three scientists in an arc. Again, I'm probably omitting some people I shouldn't be omitting, but for simplicity, I want to keep it for those three, just to understand the fundamental importance of those three scientists. So von Neumann again lays the foundation. I think I'm going to discuss his biography a little bit more formally in another episode, but I think what's really amazing about von Neumann is, of course, his contributions as a scientist, but also the times that he was in. I think reading his biography shows that there's a lot of serendipity here, right? The fact that there's a war going on, the fact that there's a Manhattan Project, the fact that they have to deal with the atomic bomb, and the learnings they get from there that gets them to create something called the ENIAC, the electronic computer, or whatever, the predecessor of today's computer. And then the idea that we can have thinking machines, because there is this idea of basic neurons and synapses akin to the human brain that can be, whose components can be learned, and whose connections can then create knowledge. This idea starts with von Neumann and then proliferates through John Hopfield, and eventually, I think, today is best represented in Richard Sutton's work. I want to mention one more thing, and that is actually von Neumann's contribution in game theory, because that is the fundamental mathematics and also logical concept that enables reinforcement learning. Now, again, there's parallels here and correlations. It's not one-to-one, but the idea that you have agents interacting with each other or the environment in a formal way, and formalizing this interaction and creating a mathematical framework that then can be borrowed into AI or reinforcement learning today, I think that's another massive contribution from Neumann, where we see the connection between von Neumann and Richard Sutton. But I guess to summarize, the fundamental idea also that I took away from the book, which the conversation towards the end about cellular automata, and the idea that you can have components that interact with each other through simple rules, and these rules get updated through the interaction with the environment, and through this interaction with the environment, you're creating a very complex, intelligent agent. Hopfield in particular demonstrated that collective computational properties can emerge from simple components. And that's the same idea in Richard Sutton's work, that you can have collective computational properties. In other words, you can have you can have an adaptive agent that can adapt to the environment from simple components, from simple interactions. In Sutton's work, it's the reward, which is a corollary to the goal that the agent has. And that simple reward, for example, just do something which is, gets you a little bit more entropy, for example, or do something that's more interesting, or do something maybe akin to Stefan Wolfram's ideas. Make sure you always have two neighbors that are beneficial to you, or something like that. Like you can have a very simple rule and you interact in many, many rollouts with the environment, and from that interaction you create an emergent complex computational property. In other words, you create something very complex. Hopfield's idea of minimizing an energy function was then transferred into what today we call minimizing a loss function. Also, it's rooted in operations research. The optimization of any kind of system is always akin to some sort of minimization of a loss function, sometimes maybe maximization of something, but mainly it's minimizing a loss function. So those ideas, again, start with von Neumann, get amplified with John Hopfield, and today are being carried over in Richard Sutton. I think I can't emphasize enough. I mean, Sutton just won the Fields Medal, so of course the scientific community is aware of his contributions. I think most of the work in robotics today is rooted in Sutton's work. The bitter lesson is applicable not just to basic machine learning, but to any kind of AI system. That, in particular, also the idea of open-ended learning. I'm going to talk about this a bit more in future episodes. But in this case, I just want to emphasize the importance of John Neumann. I think as I'm discussing his biography and his life and his contribution, and I think it's a great example of how a great mind in the right time can lead to really interesting results. I think the purpose of this podcast is to give people a sense, so it feels like to run a hedge fund. So why are we talking about biographies, John von Neumann? I think von Neumann, of course, it's the man from the future. He is a symbol for Silicon Valley. He's a symbol for progress. He's a symbol for technological innovation. I think some of the big learnings from the book that I'd like to mention here, one is, don't underestimate the math. Everything that computation and AI and engineering and physics is able to do today, all is rooted in the language of mathematics, because that is the language. That is how we communicate with with each other, and in particular with machines. Machines don't understand any other language, so we better keep grinding at the math. So that's definitely one big takeaway. I've spoken about this before. Some of the biggest contributors, whether it's von Neumann or Turing, they've all been mathematicians actually by trade. So that's number one. I think number two, we are in a time, I think, in an arc that has started with von Neumann, his contributions in game theory, interactive agents, and then in particular his work on probabilistic logics and the idea of simple rules leading to complex computational outcomes, then carried forward by John Hopfield, and now even carried even further by Sutton. I think this is the arch we're on, and we're going to get to a point where we're going to get superhuman intelligence simply because the agents that we're building are interacting with nature in a much more at much bigger scale. That's it. So it's not that we're not smart enough, or that these machines can take us over because we have some smart algorithm or anything like that. Actually, these machines don't need to understand themselves. They don't need to understand anything about the world. They don't need to know anything about us. All they need to have is the right rules and the right rewards and enough exposure to nature, whether it's through synthetic data or real data, ideally with both, and they will eventually surpass our intelligence in a sense that they will be able to adapt and solve problems at a much faster and much higher scale than we can. Thank you.